MATU 206, Week 4, Chapter 3, Sections 4 and 5. We'll start out looking at exponents and some of the rules that there are that go with exponents. An exponent is made up of a base, a number, raised to a exponent, and so the a is the base, the n is the exponent, and together a to the n is called a power. What it means is a to the n is just you multiply the base by itself n times. So if we had 3 to the 4th power, what that means is we multiply the base 3 times itself 4 times. So that'd be 3 times 3 is 9, times 3 is 27, times 9 is 81. A to the 1st power is just a because you're multiplying a by itself only once. There are several different exponent rules. This book is calling them theorems. This one is it is a product of powers, and the powers happen to have the same base. So when you have a product of powers that have the same base, you add the exponents. So if I had 4 to the 3rd times 4 to the 5th power, I have the same base multiplied together, so that's a product of powers. I get to add the exponents, so that'd be 4 to the 3 plus 5, which makes 4 to the 8th power. So that's product of powers. This one, I have a power, a to the m, raised to a power, so the base of the power n is a to the m. This is called power of powers. And what this means is I have a to the m n times. So if I had 3 to the 3rd to the 4th power, this is the base for that. So that would give me 3 to the 3rd times 3 to the 3rd times 3 to the 3rd times 3 to the 3rd. So that's 3 to the 3rd, the base, 4 times. And each one of those then is 3 times 3 times 3. 3 times 3 times 3, 3 times 3 times 3, and 3 times 3 times 3, and they're all multiplied together. So 3 to the 3rd to the 4th gives me 4 groups of 3 times 3 times 3, or 12 threes multiplied together, which means I can take 3 to the 3rd to the 4th, and the rule says I just get to multiply the exponents. So 3 to the 3rd to the 4th is 3 to the 12th, which is 3 times 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 3. This one is, I'm used to it going that direction, so this is a product, and this is a power of a product. So this is the power of a product rule. And what it says is since we have a times b, we can just take the exponent, and give it to both factors, and end up with a to the n times b to the n. Or if you have a product and the bases are different but the exponents are the same, then you can pop out the exponent. So if I had 3 to the 4th times 5 to the 4th, the bases are different, but I can do 3 times 5 to the 4th power since I have the same exponent. I can go that way. Or if I had 4 times 6 to the 3rd, I can give the exponent to both of those. So that would be 4 to the 3rd times 6 to the 3rd, power of a product. This one is a quotient, because the answer to a division problem is quotient with the same bases. So it's a quotient of powers, and it's the inverse of product of powers. So product of powers, we add the exponents with a quotient of powers. Um, Multiplication and division are inverses, so instead of adding, we will subtract. So multiplication and division are inverses, inverse operations. And so when we multiply, we add. When we divide, we subtract. So if I had 7 to the 8th power divided by 7 to the 3rd power, since the bases are the same and I'm dividing, I would do 7 to the 8 minus 3, or 7 to the 5th power. Usually when I teach my middle school students, I also include the quotient of powers. So this is a quotient, or the power of a quotient rather, and C, and what I can do is give that, so that would be a to the c divided by b to the c. I also talk about the zero power, and this is anytime you raise any value to the zero power, other than you get 1. And we talk also about negative exponents. And in order to do that, the negative on the exponents just says do the opposite of multiply, which is divide. So when the exponent's on the negative, you move the term to the denominator, unless of course it's in the denominator already, and then you move it up. So that would be a to the positive c. This stuff won't show up in your homework, but can't just give you some of the exponent rules. So write each of the following with only one exponent. So what we have here is 2 to the 6th times 8 to the 5th times 16 to the 3rd. What I notice is if I have 2 to the 6th times 8 to the 5th times 16 to the 3rd, I can break this 8 down to 4 times 2, and I can break the 4 down to 2 times 2. And so what I really have is 5 2's there and 3 2's there. So 8 to the 5th really comes out to be 2 to the 3rd to the 5th. So I have 2 to the 6th times 2 to the 3rd, because that's 2 to the 3rd for 8. And 16 can break down to 4 times 4, which is 2 times 2, which is 2 times 2. That's 4 2's multiplied together, so that's 2 to the 4th, and that's raised to the 3rd. So what I've done is I've changed 8 into a power of 2, and I've changed 16 into a power of 2. And now I have 2 to the 6th. I have a power of a power, so I multiply the exponents, so that becomes 2 to the 15th. I have another power of a power, so I multiply the exponents, so that becomes 2 to the 12th. And then I have product of powers here, same base, so I get to add the exponents, so that comes 2 to the 6th plus 15 plus 12 equals 21, 2 to the 33rd power. This one, 9 to the 4th times 36 to the 5th, divided by 3 to the 18th. 9 to the 4th breaks down to 3 times 3, so that's really 3 squared raised to the 4th power, times 36 to the 5th. Well, 36 breaks down to 6 times 6, which is 2 times 3 and 2 times 3. So that's 2 squared to the 5th and 3 squared to the 5th. And then I need to divide that by 3 to the 18th. Well, I have power of power here, so that's multiplying 3 to the 8th times 2 to the 10th times 3 to the 10th. I have the same base multiplied here, so that's 3 to the 18th times 2 to the 10th divided by 3 to the 18th. Bring that down. And now I see that I have 3 to the 18th divided by 3 to the 18th. I get to subtract those exponents, which leaves 3 to the 18 minus 18 times 2 to the 10th. And 18 minus 18 is 0. So I'm going to come over here. So that means I have 3 to the 0 times 2 to the 10th. Any value raised to the 0 power is just 1, so I have 1 times 2 to the 10th. And the identity property of multiplication says I can multiply any value by 1 and not change that value, so the 1 goes away. So I end up with 2 to the 10th as my answer. Multiplication using expanded addition. This is a 3 in the hundreds place, and that's why I can have 4 times 300. This is a 6 in the tens place, so that's plus 4 times 60, and this is a 7 in the ones place, so that's plus 4 times 7. 300 really is 3 times 100, so I have 4 times 3 times 100 plus 4 times 6 times 10 plus 4 times 7, and this is all place value. So this is 4 times 3 times 10 squared plus 4 times 6 times 10 to the first plus 4 times 7. Well, that's 12 times 10 squared plus 24 times 10 plus 28. 10 squared is 100, so that's 1200. It's a 12 in the hundreds place, plus 24 in the tens place is 240, plus 28, and I can then add them all up, and so that's 1440 plus 28, and that would be 1468. Lattice multiplication is another thing where you build this lattice work, and it's really easier for students to understand. The problem is it takes paper, and they have to draw the lattice. And imagine multiplying 38,472 times 6,397. You're drawing a lattice that's huge because you have to have a 5 by 4 grid. Let's see. 1, 2, 3, 4, 5, and then you have to have 1, 2, 3, 4, and you have to draw your little diagonals in there. And the better you draw it, the easier it is to work with. And so you'd have 3, 8. Oh, I guess you have to keep going. 3, 8, 4, 7, 2, and 6, 3, 9, 7. And then you just do 6 times that is 12, and 14, and 24, and 48, and 18. And that would be 0, 6, and 21, and 1, 12, and 24, and 0, 9. And I missed that one, 1, 8, and 6, 3, and 36, and 72, and 27, and 14, and 49, and 28, and 56, and 21. The nice thing about lattice is you don't have to worry about carrying and things like that. It just kind of works out. So all you really need to know is your multiplication facts of 0 through 9. The problem is now you got this big mass of problems, and the bigger you get, the more space it takes and the more you have to do, because now you just add down those rows, and that's 6, and carry the 1, and I've lost even my rows, so I can't even do this at this point. This problem that's already written here is much better. It's 2 times 4 is 0, 8. 3 times 4 is 12. 2 times 1 is 0, 2. 3 times 1 is 0, 3. Then I add down, so 2. 8 plus 1 is 9 plus 3 is 12. So I do have to carry here, but then that's 3. And so my answer is 322. I just kind of read it around the corner. Lattice multiplication is really kind of cool. As I said, the problem with it is the space it takes and the need to draw the lattice. Otherwise, it's a much more accurate method of multiplication for most students. Short division just means you're not carrying it down, and it really only works with single digits as your divisor. 5 goes into 2. No. 5 goes into 28. Yes, 5 times. And you can do 5 times 5 in your head, and then do the 28 minus 25. And you put your instead of doing 25 and 3 and bringing down for an 8, you just take this 3 and you stick it next to that 8. So then 5 into 38 goes 7 times. 7 times 5 is 35. And again, instead of putting 35 there and putting 3 and bringing down the 0, you just take this 3 and you tag it next to that 0. So then 5 goes into 36 times. It's really just a little shortcut, a lot of mental math. Base 5 multiplication table. Again, if you multiply 2 times 3, we would say 6 in base 10, but since there is no 6 in base 5, you have to take a group of 5 out. So there's the group of 5 with the 1 left over that stays there. And now we're going to multiply 2, 1 in base 5 times 3 in base 5. And remember, this is the 5's place. You have the 1's place and the 5's place. So you have a 2 in the 5's place. So that's 2 groups of 5 that you're multiplying by 3. So we have 2 zeros. So 3 times 1. Well, that's 3. That's easy. But 3 times 2 is, or 3 times 2, 0, really, is 6, 0. We have a group of 5 we have to take out, so we take that group of 5 out and we have 1 left over plus this 0, so that's where the 110 comes from. And we can add the 110 plus 3 to get 113 base 5. And notice when I'm saying this, it's 113. It's not 113 because that is all decimal language. It is 113 base 5. To divide, the easiest, most straightforward way to divide is to try to take groups. And so we're going to use groups of 10 or 1, 0 with 4, 3 base 5. And we're going to have several of these groups as we subtract out until we get to such a point where another group of 1, 0 times 4, 3, 5 won't fit. So we say we multiply by 10, which just means put a 0 on the end of it. So we have 10 of them, and we do the subtraction. We have another 10 of them will still fit, so we do the subtraction. 430 will still fit, so we have another 10 of them, and we do the subtraction. And we end up with 401. Well, 430 won't go into 401. So now we're estimating at 2, and 2 times 43 base 5 gives us 141. Because 4, 3 in base 5 times 2. 2 times 3 is 6. We don't have a 6. We have to take a group of 5 out and carry it over. And 6 minus 5 is 1. 2 times 4 is 8 plus 1 is 9, but we can't do that, so we have to take a group of 5 out, carry it over. That leaves a 4. And then we have one group of 5. That's where the 141 comes from. We subtract it. We end up with 210. I see that 141 will be able to take out of there again. So we have another group of 2. And when we're done, we're left with 14. And that's a remainder that's left over. So then we can add up 10, 20, 34 times 435 will equal. So there's our 34 with our remainder 14. And we get it by doing this extended subtraction in our division. Multiply binary is fairly straightforward. If you have a 1, you just rewrite it. And then, so we have 1, 1, 1, 1 in base 2. So that means we have a 1 in the 1's place. We have a, so that's 2 to the 0. That's 2 to the first place. So we have a 1 in the 2's place. This is 2 squared, and this is 2 cubed. And so really what we have is, if we're going to translate it, that's an 8, that's a 4, that's a 2, and that's a 1. 8, 12, 13, 14, 15. In decimal, that's how you represent 15. just extra. Um, Mental mathematics. We can add mentally. One trick for adding is adding from the left. And so you just say, okay, well, 70 plus 20 is 90, and 6 plus 5 is 11, and then you can go 90 plus 11 is 101. It seems to be mentally easier to add from the left than to add from the right and do 11. Carry the 1 because now you've got 1 plus 7 plus 2 you're all trying to juggle. Another method of mental addition is breaking up and bridging. So we start out with 76, but again, we're going to just add 20 to it. So that's 76 plus 20 makes 96, plus 5 more gives us the 101. We can trade off. We can say, okay, 76 is almost 80. So if I add 4 to that, I do get 80, but if I've added 4, I have to subtract 4 from someplace. So now I have 80, and 25 minus 4 is 21. 80 plus 21 is 101. Using compatible numbers, this is where you just look to group. So 130 plus 70, well, that's relatively straightforward. It's 200. You have 50 and 50, that's 100. And so you have 200, and that extra 20 is 320. Make compatible numbers. So I know that 76 and 25, well, 76 is 75 plus 1, isn't it? 76 is 75 plus 1. I know 25 and 75 is 100, plus that extra 1 is 101. So it's a really familiarity with numbers and how you want to play with them and juggle them together to be able to add. Mental math with subtraction. You can break up and bridge again. And so 74 minus 20, I know is 54. And then, so there's the 20 that I got from there. And then 54 minus 6 is 48. I take that 6 ones away after that. So I broke 26 into 20 and 6 and did 2 separate subtraction problems. Trading off, I know that getting 26 to 30 would help. So what I did is I added 4 to both of them. 26 to plus 4 and 74 plus 4. I add 4 to both of them. The subtraction of 74 and 20 minus 26 is the same result as 78 minus 30, just adding 2 to both of, or 4 to both of them. But it makes it so that 78 minus 30 is an easier subtraction to do in your head mentally than 74 minus 26. If you see zeros at the end, you can drop the zeros, then do the mental math, and then add the zeros back. Adding up, or cashier's algorithm, or the correct way of counting change, which is a lost art. And that's what this is about. This is subtraction. If you buy something for $11 and hand the clerk a $50 bill, what the clerk's going to do, or should do, is start out at 11 and work up to, well, we have 15 is a nice number. So they're going to say 11, 12, 13, 14, 15 as they're giving you $1 bills. Now that they're at 15, because you're always trying to get to the next 5 with the ones, and now they're 15, they're going to try and give you a 5 to get to 20, and then the next thing would be a 10 to get to 30, and then you can give a 20 to get to a 50. When you're using the cashier's algorithm, you always start with the smallest value. So if you're even with coins, if you had paid $2.56 for something and you'd given them a $10 bill, I would start with pennies. So I would give you 4 pennies, and then I would say $2.60 because 4 pennies makes that. Now I'm looking to get to a 75, so I would give you 1 nickel, and I would say $2.65. I'd give you 1 dime and say $2.75, because then I can give you 1 quarter and say $3. Next thing I'm going to do is work with dollars. So I give you $2. and say $5, and then I give you a one $5 bill and say 10, and that's how I would count back your change. I really don't know how much change I gave you, but I do know that by counting up to your amount, I did give you the exact right amount of change. Mental math with multiplication. You can do front end multiplying, so 78 times 4 is 70 times 4. So I'm going to do 70 times 4, get 280, and then I'm going to do the 8 times 4, get 32, and I can then add those together to get my 312. I can use compatible numbers. So 2 times 8 times 5 times 40 times 5. One of the things I may do is, oh, I know that 2 times 5 is 10, so that's cool. I know that 5 times 40 is 200. I also know that 10 times 200 is 2,000. And then I can multiply that by 8 and get 16,000 in my head. Think money. So 84 times 25, you can always think of it as 84 quarters. So 25 is pretty easy because we can multiply or divide out. So that's 84 times 25. What I would do is it takes 4 quarters to get to a dollar, so I'm going to divide 84 by 4. Instead of multiplying, I'm going to end up with 21 and $21. But it's dollars, so I have to add the 2 zeros. Dividing, I can break things up, so I see that 8 goes into 56. I know that's 7 times, but that's a 7 in the hundreds place. And I know 8 goes into 48 6 times in the ones place, and I have to put my 0 in there. So on the unlikely instance that it works out to be something like that, if you notice it, you can break up the dividend using compatible numbers. 105 I know is 90 plus 15, and I know that 3 goes into 90 30 times. I know 3 goes into 15 5 times, and then I can just add those two to get my quotient. Now this is estimation. How do I estimate numbers? Front end with adjustment. So the front end with adjustment says add the front ends. 4 plus 5 plus 2 is 11. And it's in the hundreds place, so I have 1100, and I can adjust 22 and 31. That's roughly 50, and that's roughly 70, and I can do 70 and 50 is 120, plus that 1100, and I know I would have about 1220 there, and that probably should be the wavy line saying it's approximately that. It's not exactly that. It's all an estimation. And when you have estimations, it's not the equals, it's the wavy equals. Group to nice numbers. So, and this is probably my more go-to method when I'm doing this. I go, okay, those 3 make about 100, and those 2 make about 100, so my sum is about 200. You can also cluster. So that's about a 5,000. That's about 5,000. They're all about 5,000, and so there's 5 of them, and 25 or 5 times 5 is 25 with 3 zeros, so it's 25,000. You can round. So that rounds down because I'm looking at the thousands place, and the 2 is less than 5, so I'm going to go to 7,000. I'm looking at the 3, and the 8 is greater than 5, so I'm going to go up to 4,000, and I can then do the subtraction. Using the range, so I can find the low estimate, which means I'm going to go down with both of them. So 7,000 plus 3,000 is 10,000. And the high estimate, I'm going to go up with both of them. 8,000 plus 4,000. So I know that the sum will come between 10,000 and 12,000. Estimation for multiplication and division. Front end estimation, I'm going to start out and say 400 times 9 is 3,600. 70 times 9 is 630. And I'm really not going to worry about the ones place at this point. I'm just going to add those two values together and and that's my estimate. And again, it should be squiggly lines. Or compatible numbers. 3,752 is really close to 3,600, and I know that 6 goes into 36 6 times with those 2 zeros left over. Quick and easy. Again, this is estimation. Reason we need to check student how to estimate is because now that they're using calculators so much, I tell them the best use for a calculator is making a bigger mistake that much faster, because the students plug numbers into a calculator and they get an answer. I'm sorry, they think it's right, whether it makes sense or not. We need to teach them estimation so they can look back. Remember George Poya in the first chapter and his um, method of problem solving: understand, plan, solve, and then look back. This part's often skipped, but look back. Two things they look back for is, am I answering the question I'm asked? And the other thing is, does my answer make sense? And that's where estimation comes in. They need to be able to estimate these so they can look and see if their answer is in the ballpark. If it's close to their estimation, then they're good to go.